Hello everyone, welcome to today's Solution Shareout webinar. My name is Guy Bottle, I'm the Product Marketing Manager here at Octon for the Geomagic portfolio, and today we are joined by some special guests. We've got GoMeasure 3D, one of our software resellers based in the US, and today they are going to be spending some time discussing the benefits of combining Lidar scanning with 3D scanning software, in particular Geomagic Design X and Geomagic Control X. A couple of housekeeping bits before we get started. If you haven't used GoToWebinar before, you should have a control panel on your screen that just hovers over the screen share that you should be seeing. There is a question area there. If you have any questions as we run through this presentation, feel free to drop them there. The live portion of this presentation is going to last around 45 to 50 minutes, which should leave us 10 or 15 minutes at the end to answer any questions that you might have. But without further ado, I'll pass over to Art and Paul from GoMeasure to take you through what they've got to show today.
Awesome. Thanks for the intro, Guy. So as Guy mentioned, my name is Paul Motley. I've been with GoMeasure 3D for 15 years, and in those 15 years, we've scanned a lot of different things in the company, and I specialize more on the reverse engineering and inspection side of things. We also have Art with us, and Art, if you want to intro yourself a little bit.
Sure. My name is Art. I've been with GoMeasure 3D with them for over 3 years. I'm coming from a background in education at the university level, and I've been with Artec scanners for over 6 years at this point. My experiences in historical preservation and large-scale captures with Lidar scanners, but also in smaller scanners and historical preservation of artifacts, using also these assets in AR and VR applications and education as well.
Perfect. So just to give you a little bit of an intro as to who we are, GoMeasure 3D specializes in 3D scanning technologies, mainly 3D digitizing hardware that encompasses the Artec product line, as well as various other 3D scanning solutions. We also provide quite a few different softwares, Geomagic being one of the main ones that we use for reverse engineering and inspection. And we work in commercial, educational, and government applications. So now that you understand a little bit about who we are, let's go ahead and jump into today's presentation and talk about scanning large area objects with the Ray 2 and the Artec Leo, and how we can actually efficiently process that data using the Geomagic softwares. So Art, I'll go ahead and hand it back over to you for the scanning portion, and then I'll jump back in here in a few minutes to talk a little bit more about Geomagic Design X and Geomagic Control X.
Yeah, so we'll be talking today about a problem that you all came here for, to try to understand what a large-scale capture can do for you, especially with Artec and Geomagic software. Some of the tools that we'll be discussing today will be Ray 2, the Leo. Those are two different scanners, scan using different technologies, as well as Artec Studio, the software that comes with these scanners. And then, of course, with Geomagic Design X and Control X, two very powerful tools for going from scan to CAD and then inspecting our models. So the problem that you may be interested in would be, how do you capture really large scale spaces? And Paul, you can skip to the next slide. And
Come on.
Can you hear me now?
Yes, yeah, we can hear you.
Okay,
Sorry
great.
about that.
Yeah, that's all right. Sorry about the little technical glitch here. So as you can see in this video, we've got really large spaces you may want to scan for retrofitting objects to something like this flood wall enrichment, or potentially for looking at change over time, or to really understand the scale and the sizes of these places. And also, if you're familiar with the technology, you may have some questions about what is the state of this technology today. So with the Ray, we've got a very quick capture that we can make, and we can process this data in a matter of hours and make these scans in under an hour these days. And then we could take these massive files, these massive point clouds, and work with them in the software we'll be also talking about today. So to talk a little bit about our tools, if we just look at the scanner side of things, the Artec suite of software and hardware is being developed every year, and what we see now is these smart scanners that have built-in hard drives and built-in computers. So on the next slide, Paul, we could take a look at these two scanners. The Ray is a Lidar scanner that's stationary, that can give you accuracy of up to 2 millimeters at 10 meters and a resolution of 3 millimeters across 130 meters, or anywhere from half a meter to 130 meters. You can do this very, very quickly. And the Leo is a structured light scanner. This is the handheld scanner that has a battery and a computer built in, and it allows you to very quickly turn it on and do a particular scan of an area, and then later in the software align those two scans and get up to 100 micron accuracy with this scanner, and it gives you a lot more flexibility to be able to scan around an object, as you may imagine with a stationary scanner would be harder to do. So we, Geomagic 3D, we are a reseller for Artec, and we do demos of these products, and so we're today bringing together the expertise of the scanning technology with Geomagic software. Paul, if you want to introduce that a little bit.
Sure, yeah. So, the two primary Geomagic softwares that we're going to be taking a look at today for working with this data that comes off of the Ray 2 and the Leo are going to be Geomagic Design X and Geomagic Control X. So Design X is an extremely powerful reverse engineering platform that allows us to take these massive scan data sets and process them down into usable CAD information that we can either work with directly inside of Geomagic Design X or export out using our live transfer tools into native CAD packages that you may already be familiar with, like SolidWorks, CATIA, softwares along those lines. Additionally, we'll take a little bit of a look at Geomagic Control X, which is what we use for inspecting this 3D scan data. We can inspect it directly just using the scan files themselves, or we can also take pre-existing CAD data and then compare the scan files to that CAD geometry directly. So to get started, what we're going to see initially is Art talking about scanning and creating information like this. And then from there, what we can do is turn it into CAD geometry like you can see here and export that out into, for today's example, it's going to be SolidWorks. So I'll pass it back over to you, Art, and we can talk a little bit about the solution as far as scanning with Artec goes, and then I'll jump back in and talk a little bit about Geomagic.
Yeah, so why we're putting this on today is because what we've seen is an advancement in this technology to a point where you no longer need a computer. You don't need to be tethered to a device to be able to go out and very quickly capture massive spaces. So our solution is a workflow that allows you to, as you'll see in the scan data we'll be showing you in a little bit, capture a massive wall that took me under 20 minutes to scan with 9 different positions. So I was able to move the scanner very quickly and under 20 minutes capture the 3D scan data. Now that was then triangulated in Artec Studio software, and then our mesh was imported into Design X, where we used all of the tools that you're familiar with to create CAD geometry, these CAD models, and then further inspect that in Control X. So I have a little presentation about the scanner I could show you. Paul. All right, I think I'm unmuted here. You can see here with the array, once you turn it on, it takes less than 2 minutes to complete a scan in 360. This captures everything around you in one scan, but the scanner itself has a vision system and a GPS tracker. So as you're done with one scan, you would just pick up the scanner, move it to another location, and complete as many scans as you need to get around all of these different angles. So what you're seeing here is some scan data from Artec Studio. This has been processed out into a mesh, but the scale is all there. The scan data is coming in already positioned on like a GPS coordinate, as well as calibrated to the scale of the real world object. So the array right here, it comes in a hard case, and all you do is with a quick release, you're able to very quickly mount it on a tripod. What you have are 2 batteries in here that can be hot swapped and allow you to continue scanning without having to shut the scanner down if you do run out of battery life. I haven't run out of battery life yet, but you also have a really fast flash drive in here that has 256 gigs, and that is the process of capturing and transferring your scan data to your computer. You would just shut the scanner down, plug that into your computer, and import it in Artec Studio software. I want to show you some of the scan data as it comes into the software. So I think we have a slide for that. So when you first bring in the scans, it's a matter of just dragging that into Artec Studio, and this is what it looks like. There are 1.2 billion points in these 9 scans. If we zoom in a little bit closer, you can see some of the positions of my scanner. So in this slide, there are some circular cutouts you can see on the ground there, and those are the different locations I just moved the scanner from. So 2 minutes in one spot, my scanner gives me a green light. Once it's done scanning, I just pick it up, I don't turn it off, and the scanner is watching like a VR headset with these 360 cameras on the corners where I'm moving it alongside with that GPS information, and it's able to do a registration on the scanner. So it moves alongside that previously recorded data and then lines the next scan into the scene. So all I have to do is run 2 algorithms in Artec Studio, and that is my finer registration called global registration, and then some kind of triangulation. So I've got different options if I want, instead of a point cloud, a mesh to export. So what we can see after processing the scan data is something like this. And in this case, I've cut the trees out and a couple other unnecessary things, and I've separated the wall, the bridges, and the street into 3 different layers. And I'm able to do all of this in about an hour with the software. Depends on your computer. Of course, I got this laptop that I did it on, so we're still doing some testing. But overall, it's quite an amazing improvement in this technology, in that I didn't have my laptop out. I was able to see that everything was working properly through the screen that I have on the scanner, and I was able to, in 20 minutes, capture this massive space and 9 different scans, and then bring it back to the office for measurement for this snapshot of that real world space, where we can then do many more things with it. Paul, if you want to show a little bit of the CAD creation process, I think I covered everything I wanted to here.
Perfect.
Anything
Yep. Yeah, no, I think that's great, Art, and that covers a pretty good idea of how efficiently you're able to go in and capture all this geometry with the Artec Ray 2. But now really comes the challenge of within about an hour and a half, right? You can capture all this geometry and then hand it to me, but we're dealing with hundreds of millions of polygons. So with that, if anybody's familiar with trying to import that type of data set into a CAD modeler, it's virtually impossible for most modelers to be able to handle that level of geometry. So what we're going to talk about next is taking this information, pulling it into Design X, and then being able to extract out the information that we really need from that model to, in turn, either use it directly inside of Design X or export this over into SolidWorks. So some of the key tools for Design X that I want to cover is our process designer. I'll give you all a basic introduction just to the fundamentals like mesh sketching, some of the really useful tools inside of Design X like the feature extrusion and the Design X wizards. Again, we'll talk a little bit about transformation of various objects, and then take all of this over into SolidWorks for this example using our live transfer tool. So let's go ahead and jump over into that. So you can see here, this is Geomagic Design X. And inside of Geomagic Design X, we have quite a few different tools that we can use to efficiently recreate a model like what you're seeing here, where we've got our scan data overlaid on top of our CAD model. So again, Art's already talked a lot about the scale of this, but just to kind of give you an idea, we're dealing with a very large file with lots and lots of information that we want to be able to turn into CAD geometry as efficiently as possible. And one of the biggest challenges is just breaking meshes down into a way that's efficiently usable for us in our reverse engineering process. And with that, one of the first and one of the most beneficial things with Design X that I think of when it comes to working with larger meshes is a tool that we call our process designer. So let's actually go ahead and start looking at that real quick. So I'm just going to take a sample of one of these piles from this bridge, and we're going to open up the process designer inside of Geomagic Design X. And what this tool allows us to do is take repetitive processes with meshes that we may do over and over again, such as decimation, any sort of segmentation that we want to do, as well as our healing wizard, which basically just cleans up our mesh, and put all of these into a macro that we can efficiently run so we don't have to do these same things over and over again. So I'll show you inside of these tools, like for instance, decimation, which is the ability for us to take a large mesh file and then maintain the accuracy and a lot of the resolution while eliminating a large portion of the meshes. We can then use our healing wizard to clean up a few things, and then do our automatic segmentation, which we'll talk a little bit more about here in just a couple of moments. But that auto segmentation makes it really easy for us to extract CAD geometry out of our parts. So now you can see once we've built out that process, it's a very simple task of actually running that on our model by simply selecting the mesh that we want to run our process on. And then once that's done, we can go ahead and check off our process, and you can see here in just a couple of seconds, we can run that process on this pile. Obviously, for a larger section of the mesh, it's going to take a little bit more time, but just for the time constraints with this webinar, we're showing it as an example here on this pile. So now we've got our region set up, we've got our mesh decimated to where it's a little bit more efficient for us to work with. So with that being said, let's go over and just talk about some of the more simplistic aspects of Design X before we get into some of the more complex topics. And the first one that I want to talk about is just basic mesh sketching. So if you're familiar with modeling inside of any sort of CAD software, traditionally you start with a two-dimensional model, you sketch out that 2D information, and then you'll extrude that into some sort of 3D shape. And we can do that very easily here directly inside of Design X, but it's a little bit more powerful than just sketching. So what we're showing right here is setting up a mesh sketch. And what that allows us to do is take a cross section of a particular section of our mesh and build out 2D geometries on that particular section. Not only can we do it in just one 2D slice, but we also have the ability to set up what we call a silhouette range. So when you want to best fit information through a given area to make sure that's as accurate as possible, we can use that silhouette to really make sure we're capturing all the information that we want to reverse engineer. From there, we can go ahead and use various CAD features inside of Design X. One of the powerful things about this mesh sketching is, as you can see here, we can use that mesh sketch to very accurately snap CAD geometry onto these individual 2D sections. We're not limited to that, however. As you can see, we can just draw any sort of standard geometry that we so choose inside of Design X. And one of the powerful things about this software is it is in and of itself a really powerful CAD modeler. So not only can we extract geometry directly from our sketch, or from our 3D scan data rather, but we can build new geometry. So if we want to build out lines or arcs, or if you're used to using any sort of filleting tools, any sort of trimming functionality, your circular sketch patterns, linear sketch patterns, all of that can be very easily done here inside of Design X. So let's just finish cleaning this little section up here for our example. We'll go ahead and just trim off a little bit of this geometry. And now we can go ahead and extrude this 2D shape out into a solid object. So to do that, we'll go ahead and turn back on our mesh. And this is another one of the really powerful features of Design X is with our mesh as a reference in the background, we can very easily use that to extrude to specific positions, or we can just define how far we want to extrude a shape based off of a numerical value. So one of the challenges with reverse engineering quite often is trying to deal with real-world parts that have imperfections and make decisions on how you need to accurately reverse engineer that model based upon what the actual goals are. So whatever your need is, there's a lot of flexibility in Design X to either model exactly to the part or to make it more true to what the CAD shape should be. So that's kind of the fundamentals. That's very similar to any sort of CAD modeler that you may or may not already be familiar with. But we can take it one step further with Design X and not only do basic 2D sketching, but use some of our wizards to really streamline this process and make it as efficient as possible. So let's go back to the example of this pile here and use our extrusion wizard to really efficiently build out this geometry. So you can see if we go into our extrusion wizard tool, we're able to very quickly and easily capture those regioned areas that we created earlier using our segmentation. And with this, Design X will automatically identify what type of feature we're trying to create and how big that feature is supposed to be. So you can see here we've got a rough model of what that part's supposed to look like, but we're missing a few bits of information, right? So not only can that wizard be used to create data, but we can also use it to, say, cut off areas that we need cut off on that particular model. So just by selecting those lower planes, it automatically understands for us that we're trying to cut out that particular area, and we can just use our Boolean operations to very efficiently figure out where this needs to be cut, and then go ahead and cut that data off of our pre-existing extrusion that we just created. So moving on from this, not only can you use extrusion tools like we're seeing here, but we can also do some interesting things, I feel like, with primitives. And this gives you kind of an insight into the fundamentals of Design X. So if we build out this cylinder here real quick, you can see this is just kind of a basic cylinder that's a little bit larger than it should be. But inside of Design X, we have a fully parametric modeler. So with that, you can see that the cylinder is actually made up of a 2D sketch. And with that sketch, we can modify it as needed. We can also modify the revolve itself. So instead of it just being a basic model, we can merge that into the solid bodies. So you can see here in just a couple of seconds, we're able to really efficiently recreate this pile and this cap for the underside of this bridge using the power of these Design X tools. So another thing that I want to just cover real quick that I think was really important for this particular project was simply the transformation tool inside of Design X. Quite often in reverse engineering models, you have repetitive geometry, like for instance, these piles, and being able to essentially copy and paste this geometry around our part to build up that full model is really powerful. So for this example, we're just doing a basic rotation and translation. However, you can see here in the methodology that not only can we just physically move this part, but we can also align our transformations based off of datum structures or to the scan data itself. So you've got a lot of different tools in here to make sure that you're accurately modeling this part as accurately as you need for your particular application. So now that we've built out some of the geometry and you have a good idea of some of the fundamental tools here inside of Design X, probably the most important thing for a lot of people is getting this into your native CAD modeler. And that's where the power of live transfer with Design X comes into play. So as you can see, we've been modeling all of this geometry in a parametric fashion. And we have all of this data that we probably want to get into our CAD modeler. To do that, it's a very simple and straightforward process. You can see we have this live transfer tool. And for our example today, we're going to go ahead and just transfer all that data over into SolidWorks. So when we press live transfer, it's going to automatically open up SolidWorks for us. It's going to model all of this geometry for us as if we're modeling it directly inside of Design X, or inside of SolidWorks rather. So you can see Design X is transferring all of that geometry that we created here in Design X over into SolidWorks. It's building it all parametrically, so we have our parent-child relationships, and we have all of this geometry that we can modify inside of SolidWorks as needed, as if it was created in SolidWorks, because that's how this process works. So you can see in just a matter of a few minutes, we're able to really quickly and easily break down really large scan data sets, convert those scan sets into usable CAD geometry, and then automatically transfer that geometry over to Design X. So now let's go ahead and talk a little bit about inspection. So we've covered Design X, we've covered creating this CAD geometry, but another really important feature is being able to analyze this information. So for instance, with this flood wall, we may want to see where there's various deviations on the part itself, where there may be some erosion, or if there's some sort of substrate that's causing, the wall itself to shift, say down into the earth. That's something that we want to be able to pretty efficiently analyze. And the way that we would do that is using Geomagic Control X. So let's go ahead and jump into Control X and talk a little bit about what we can do there. Okay, so you can see here, this is Geomagic Control X, and with this example, we've gone ahead and cut out a section of the flood wall from the scan data, and we're also going to just use some of that CAD information that we already created. So with Control X, we've got quite a few different tools that are really useful, and I want to start with just showing what you can do with the scan data in and of itself, where we don't even need a CAD model. And one of the really beneficial tools, say for instance, when looking at corrosion, would be our deviation location tool set. So if there's chips or erosion on this flood wall, we can very easily look at a particular example of that wall and then pull out the data that we need to understand from that. So for instance, some chips and some pitting that's on this particular section. To use this tool is very simple, very straightforward. Basically, we just select the area that we want to analyze, and then we'll go ahead and tell the software what type of features, how deep we really want to consider being a good feature or a bad feature. And then with just a couple of clicks here, we're able to identify that color map and make sure we've got all of the information that we're looking for. So you can see here, we've got quite a few different deviation locations that we're going to analyze, and we'll take a look at those a little bit further when we get into the reporting section of Control X. So in just a couple of moments, we can break down a relatively complex shape and extract the important pitting or erosion locations that we may want to analyze further in our reports. So that's something that we can do just right off the bat with the scan data alone. Now, if we have CAD geometry that we want to compare to inside of Control X, then we can bring that in. And the first thing that I really like to do that I think is probably one of the more powerful features of Control X for a lot of use cases is just a simple 3D comparison. So what a 3D comparison does is it allows us to pull in our CAD model, which would be our theoretically perfect model, and then we can tell the software what we would accept as accurate tolerancing, as well as a range of deviations that we would want to understand. And you can see here on screen that anything that's going to be inside of green means it's within our acceptable range of tolerance. Anything that's going to be red or blue is going to be either high or low based upon that range that we gave the software. So for instance here, if there's a shift in the substrate that this flood wall is sitting on, we can see that identified as these high areas indicated in red or low areas that are indicated in blue. So in just a couple of moments, we're able to really efficiently extract out that data and see it in a nice, useful fashion, because while numbers and measurements are extremely important, sometimes it's good just to be able to quickly visualize how a part actually deviates from what its theoretically perfect model would be. So we've talked a little bit here about 3D comparisons, but equally as important for a lot of applications is 2D comparisons. If you've ever looked at a blueprint, a lot of times those are broken down into 2D slices. So being able to do this exact same process in a 2D manner is really important for a lot of people. So doing this is very straightforward. We can simply just select a planar area that we want to use as a cross-section. We can set where we want that cross-section to be. So for instance, here we're going a little bit lower than halfway down this flood wall. And then once we select that area, what we're going to see is something that's very similar to the 3D comparison. It's just going to be in a 2D fashion. Again, we can adjust our ranges and our tolerances to fit our particular need. And then one thing that I like to highlight here in the 2D comparison that we can do in 3D as well, but it makes a lot more sense here for a lot of applications in 2D, is being able to use what's called our whisker multiplier. So if we look at this 2D profile, you can see that it's deviating high and low in various areas, but that deviation is so minimal, we don't have a really good understanding of what's actually going on. So our whisker multiplier multiplies that deviation by a set value. So now you can see we have a really good indication of where there are shifts on our part, where there's deviations from what the perfect example of that part is. so that we can very easily analyze this and make the notes or adjustments that we need to accordingly. So we've talked about some of the more generic, simplistic approaches, but most people in their applications need some sort of hard numbers. So whether it's lengths, widths, radiuses, things of that nature, and that's where our dimensioning tab inside of Control X comes in. So a tool that I love to use is Smart Dimension. So for instance, in this application, you can see that we can very quickly and easily snap onto various CAD geometry. And what Control X is doing for us here is identifying the type of measurement that we're trying to get it to measure, and then extracting that out for us. So for instance, here we've pulled the widths of these doors. We can pull the heights. So for instance, the ground's compressing, and we want to be able to analyze how much it's compressing. We can very quickly and efficiently analyze that based off of the correlation of our scan data to our CAD model. So to kind of go into a little bit of what that actually looks like, let's take a look at our pairing manager inside of Control X. So as you can see, it was really efficient for us to just snap all of these measurements, and Control X is immediately spitting out the information from the scan data itself. The way that it's doing this, to kind of go under the hood a little bit, is using this pairing manager. So anywhere that we have a CAD feature that is overlapping scan data, Control X is automatically extracting that information out and using it for these measurements that we're calling for. With this pairing manager, there's a lot of control. So for instance, if you're dealing with a part that may have some corners that you don't really want to be analyzed, we can shrink the amount of information around that CAD surface, or where the scan data is around that CAD surface, to make sure we're not getting any weird outliers. We can also use various sigma outlier numbers to identify how many data points in that given surface we want to use or don't want to use. So there's a lot of control in making sure that the data that we're extracting out of Control X is as accurate as we need for our applications. So lastly, before we jump into the reporting aspect of Control X, let's just show a few aspects of GD&T. For this particular application, it may not be quite as relevant, but I do think that it is important for you to see the fundamentals of when we need to apply datums to these measurements. Inside of Control X, it's very easy for us to simply set up datum structures, so references that we want to measure to, and then pull our various GD&T measurements. So whether we want to measure flatness on a part, or we want to check the position of a particular location as it's compared to a particular datum set, or if we want to do parallelism measurements or perpendicularities, we can do that very quickly and easily using Control X. So now that we've created all of our measurements, we want to put those into a place where they can be easily analyzed, and that's where our reporting structure comes into play. So it's really easy for us to just build out this report, and then with that, you can see we've gathered all of this information that we've created here inside of Control X. So whether it's these deviation location values and all of their associated measurements, some information based off of our 3D comparison information, as well as our 2D comparison, and then lastly, of course, the 3D measurements that we just created. So one thing we will notice with some of the views in this report is, if you notice, for instance, here, we'll scroll back up to our 3D measurements here. And quite often you may have views that you need to really correlate back, especially with a large surface like this, where the view didn't quite make sense for that part. Well, inside of Control X, we can very easily adjust where our view is going to be, reassign our viewpoints, and then re-update that into our reports rather, so that when you're handing this report to a particular individual, they have a very clear understanding of where these measurements are being taken and what we're actually trying to show in our data. So this is just some of the basics of Control X. This is a very powerful software that allows us to do quite a few other things. but hopefully this gives you a good idea of some of the fundamentals of how this can be used when we're dealing with data sets that are as large as, say, for instance, this flood wall. So let's jump back over here. And just to kind of summarize a few things here, the time that it took Art to scan this entire scene was roughly 20 minutes. The time that it takes to process that data out is about an hour. And then when it comes to modeling inside of Design X, depending upon your application, it could be hours, it could be minutes. As the complexity scales, so does the time. But I think a really good, easy way to break that down is in your traditional processes, if it's taking you days to model this type of information, instead here with Design X, it'll take you hours. And then from an inspection side of things, instead of it taking hours to inspect out a feature set, it could take you minutes. So we're able to really drastically reduce the time of modeling and inspecting large things like these bridges and this flood wall with the use of this particular technology. So Art, is there anything that you'd like to add into that as well?
Sure, just to reiterate some of the points, but also stress kind of how far this technology has come along in that we're able to crunch really large data sets with not only Design X in that it can take these large meshes, but Artec scanners are able to capture things quicker than they've ever been able to do before. And their software is also more powerful than ever in its efficiency and its ability to take multiple locations, align them together, and to process it out into meshes that can be varying levels of resolution and density. So if we think about where cameras have come from, like DSLRs or SLRs to DSLRs to now cell phones, we use our phones every day, and I'm sure everyone's amazed at how good our phones are taking photos these days. So much of it isn't like the advancement in optics, it's so much is on the software side, and that's what Artec and Geomagic are doing. They're able to improve the quality of the resolution, the size of those images are wonderful, but yet the file sizes are lighter than ever. And kind of the same thing in the world of 3D scanning. First of all, it's just like the quality of the hardware and the ease of use. It just works. We pop in some batteries, we turn it on, we make a scan, move it to another location, and make as many scans as we want. All of that is saved here. And when we bring it back in, the software on the Artec side is very efficiently able to process, in this case, 1.2 billion points into a mesh at whatever resolution I choose. And I have an archive of that. So at this point in time, I've got that real world space captured, and it's kind of a digital twin. I can always go back to it and make new measurements. If I missed something, I don't need to go back out there in bad weather. And I have obviously the historical kind of record of that. So as the ground shifts and things change and cracks appear, we can make more scans and compare that scan to scan. We can do that in Artec software, but also in Control X with Geomagic. So what we do is apply this scanning technology to different applications out there. And as a company, as Geomagic 3D, we're happy to get into more details about how these scanners work. I know today's demo is just kind of showing you more visuals on the slideshow, but if you want to see one of these, we're happy to talk about that more. Some of these example workflows we've recently worked on are for customers that are looking to like retrofit some new designs to older spaces. We've had a number of boating clients that are looking to scan boats, older boats or new boats, whether they're building furniture or interiors for these boats, so they've used the Ray for that, and as well as a Ray plus Leo, enable to where they have tighter spaces or really small parts that they're looking to reverse engineer. They combine these two scanners, and all of that happens inside of Artec Studio. So it's one piece of software that can handle different kinds of scan data, and also triangulate that together. So point cloud data with structured light data, and give us a really nice mesh. There are clients in aerospace, in manufacturing assembly lines, as well as, of course, certain clients we can't talk about in other industries, in government agencies. Paul, am I missing anything here?
Yeah, no, I think that's great. The only other thing that I want to add to this is, kind of as Art's mentioned, we're giving this example with this large bridge structure and this flood wall that's based where Art is in Richmond. But hopefully you can see through this presentation how these basic concepts that we've talked about can apply to all of these different applications, right? So whenever you're scanning something large, you can see that these fundamentals that we're talking about of, generating the CAD objects that we want to analyze, take this millions or billions of data points and convert that into high accuracy geometry that we can either inspect off of or just pull into our CAD modelers, can go into so many different applications. So yeah, that's really the biggest thing that I wanted to add. Awesome. Anything else that you want to talk about, Art, before we jump into questions?
No, I think we're ready to turn it over to our attendees.
Awesome. Yeah, well, hey, thank you all very much for listening to our presentation, and we'll go ahead and see what questions you all may have for us. So, Guy, I'll pass it back over to you if you want to field some of those questions for us.
Great. Yeah, thank you guys. That was really interesting. We've got a few coming in. If you've got any other questions, make sure to drop them in the questions box. We'll get through as many as we can, and we'll ensure that Art and Paul and the team follow up if there's anything that we can't get to today. So we've got one here which is more around the computing hardware. Obviously, Art, you've got a looks like quite a beefy laptop there, but can DX and CX run on laptops? What's the specs that are required?
Sure. Yeah, great question. So I run Control X, and Art can talk about this a little bit as well, but Control X, Design X, we've been running them on laptops for years. As far as specs on computers go, it is really beneficial to have a lot of RAM and a nicer graphics card. So traditionally for us, we're using, I think you've got a NVIDIA RTX model of some sort, Art. We like to stick to, like when you're dealing with large data sets like this, at minimum, you're going to need 32 gigabytes of RAM. If you could get up to 128 gigabytes, that's great. And it really just scales based off of your application. So if we're talking about Control X or Design X running, you can run it on an 8 gigabyte machine. You can run it on a pretty low end laptop if need be, but the more power you have, the more efficiently the software is going to run. So anything you want to add to that, Art?
Sure. This is the Razer laptop. It's got a NVIDIA RTX 3080 GPU. It's probably 2 years old at this point. So yeah, no issues with this. I've also run Design X and Control X on a Mac in the dual booted with Windows installed on it. So just like a MacBook Pro, and that's not been a problem. So especially with the Artec software, it also auto saves everything. And if there's, for some reason, you lose connection, you lose power, or it crashes, everything's saved automatically. So we haven't had any issues with our laptops, and because of the nature of our work, we've been, like Paul said, we've been using these for years.
Yep.
Right, thank you. We have a complete breakdown of the the specs, minimum specs, recommended specs for the different products on the Octon support site. I'll drop the link in the chat for you to take a look at in a bit more detail.
Perfect.
So we've got one here asking about the combination, well, kind of two questions that kind of bounce off each other. So combining the scan data from the Ray and the Leo, and the realistic levels of accuracy that you can achieve when running that kind of workflow. You obviously mentioned that using the Ray 2, the Lidar scanner, is going to allow you to capture much bigger areas in a much smaller amount of time, and you can then go in with the Leo to clean up slightly harder to reach areas. But in practice, what does that actually look like?
To combine scan data between Ray and Leo.
Yep.
Yeah, so we've seen an update in the software over the past year where Artec has streamlined the process. It used to be you'd have to process the two data sets separately. You have to run a workflow for Leo data, registration, fusion, and then you would take these two meshes and combine them. Artec's recently rolled out a new feature called Smart Fusion, and that's just their word for meshing or triangulation in another sense. And now what it looks like is importing the scan data from the flash drive off of this scanner. And then I use a wireless connection for this, but you can also do an SD card. And then once I've got the two data sets in Artec Studio, there's an auto alignment available or a point-to-point alignment. And then I just run that Smart Fusion so that the software can do a registration, a global registration between the two data sets and fusion in one workflow. So they've really cut out a lot of steps, and that's been an update that's happened recently. You always have your project with your raw scan data, so you can always go back and either add scan data or kind of reconfigure your project. You may want to cut out certain things and then run another triangulation and get another mesh out of it. So you never really lose the original scans, and there's a lot that you can do with that.
Yeah,
Right.
And to go the accuracy side a little bit too, it's whatever accuracy you can get off of the particular scanner you're looking at, we can in turn take that into the resolution of the files. So it's not just fixed to like the lowest resolution system, right? It's scalable based off of the data that was brought in.
That's true. You can change the resolution yourself, or the software also adapts to the highest resolution of the scan data. So.
Yep.
Great. That kind of leads on to the next question that I was going to ask on what is the lowest or most sparse point cloud density that you can convert into a mesh?
It's relative. I mean, if you, like for instance, these bridge structures, you could take that and you could have a 1 foot, or a 200, 300 millimeter point spacing and be perfectly acceptable for certain applications, right? Whereas if you're trying to reverse engineer this pin, we need that to be pretty high, a 0.1 or a 0.2 millimeter point spacing. So it's scalable to the application. One of the things that's great about kind of like what I was talking about inside of Design X with the process designer is when you're prepping out data, because let's say you're dealing with something that's, let's just ballpark and say 50 million data points for one of these files. 50 million data points is a lot of information to crunch. It's a lot of downtime waiting for processes to run, right? If we can take that file and then decimate it based off of the curvature of the part inside of Design X, what that allows us to do is, if you can imagine, for instance, on a feature like the bridge itself, those piles that make up the bridge, those are pretty uniform surfaces, right? So you can think cylinders, planes, things of that nature. We don't need a lot of data to define where that cylinder or that planar shape is. In the real world, 3 points define a plane, 6 points define a cylinder. right? So you can really space out the data in those areas. Whereas if you've got a particular part that has higher curvature or smaller features, that decimation process allows us to concentrate the data points of a file into the areas that we really need it and eliminate all of that in the areas that we don't. So hopefully that helps to answer the question as far as how many points you really need. It's relative to your application, but tools like that decimation inside of Design X really helps to make files a lot smaller than you would get them directly off of the scanner.
And just to give a different answer from a technical standpoint, this scanner's lowest resolution is a 12 millimeter spacing between points. And that is the quickest method for scanning with this, and it's under 30 seconds per scan. So if I choose that lowest resolution on the scanner and the highest is 3 millimeters, at that 12 millimeter resolution, it takes less than 30 seconds to complete a scan, and then I can pick it up, move it to another location. Overall, you're still seeing quite a lot of points because it's scanning in everything around it, but that's where the efficiency of the software, as soon as you bring it into Artec Studio, allows you to view it with ease. The software does not load all of the data. It gives you just enough that you can view your scene and you can choose to look at everything, but by default, because of running it on laptops and things like that, they can manage this data really, really well. So you don't really have to worry about how big these scans are anymore. And some people might say, well, it's too much. Maybe it's too much data. But that's kind of generally what where the market is heading, is that first you kind of overscan and then you pare it down, you crop out, erase the parts that you don't need, and then you run that meshing process. But you always have that original scan to go back to if you realize you really do want to measure something that you didn't intend to measure in the beginning.
Yeah, it's better to have it and not need it than the other way around.
Great. We've got a couple more. I think we've probably got time for one, maybe two more questions. This question here is asking about the scan registration, the scan alignment. Obviously, the scans are being aligned based on the GPS tracking in the Ray 2. Are there ways that you can align the scans in Design X? For example, if you have a different scanner model that you're using for a different area of that application.
Sure, yeah, absolutely. Art, do you want to cover any of that, or do you want me to jump into it?
Just for the sake of time, I'll just say the quick answer is yes. So you have a point-to-point alignment or an automatic alignment. So you have a variety of tools in Design X that can align point cloud data or meshes and allow you to combine that. And there's a lot of options for removing overlapping data and things like that. So that's something that we'd be happy to demo.
And I think we've probably got time for this question here. So this one's more around the inspection side of things in Control X. So when Control X accounts for the deviation, does it take an average of the surface to account for that baseline, or do you need to have dimensions added yourself for where you want to measure that deviation?
Trying to understand the question. I think I understand the question. So when you're looking at deviation of a scan file compared to the CAD model, if you're looking at like data points, so if you just got points across the surface, I believe the question is, can you define how it's correlating that information to the surface? And if that's the case, yes. Inside of Control X, with your points, you can either try to analyze based off of closest relationship, based off of normals, so more of a vector-based. So you've got a few different tool sets inside of Control X to make sure that you're accurately analyzing that data as you need to, right? Because certain applications really cater more towards certain measurement practices. So yeah, you have the full capability to do that however you need to.
Great. Thank you, Paul.
Cool.
Well, It looks like we're at the top of the hour. Art, Paul, thank you very much. For anyone on the call that wants to learn a little bit more, the scanners that we've seen, the Artec Leo that is on Art's left, and the Ray 2 Lidar scanner on his right, and Design X reverse engineering software with Control X inspection software were the tools that they use to crunch that data. The guys have got their contact information on the screen if you want to reach out to them directly. I'm sure that they will be following up very soon to answer any questions that we've missed. But to finish off, I want to say thank you very much for joining. Thank you guys for taking the time to present. Really enjoying hosting you and showcasing what this technology can do together.
Awesome.
But thank you very much. Thanks everyone for joining, and have a good rest of your day.
Perfect. Thanks everybody.